strength of the electric field is E. And two charges, Q1 and Q2, at a distance d apart, they exert a force of attraction or repulsion, and that force due to electric charge is equal to 1 by 4 pi epsilon naught Q1 Q2 by R square or D square. Okay, this is a force between two charges, and we have learned how to find where is a force, zero, etc. Similarly, near to any charge in the field, there is electric field strength. Okay, closer to the charge, the electric field strength is more. Further away from the charge, the strength is less. So electric field is equal to force upon charge. That means if a unit charge is placed over here, with what force this is pushed away or attracted towards. So that force is the strength of the electric field. Also, we have learned that, so from this formula, what do we get? The force is equal to the charge which is placed over there times the strength of the electric field. Okay, so this is what you have seen. Plus, we have seen that in the electric field, every point has electric potential energy. So, electric potential V is equal to electric potential energy experienced by unit charge. Potential at a point is the electric, this is energy, this is electric field. So, I write energy. Which energy? Electric energy. Electric potential energy. Electric potential energy explain, okay, by unit charge is called potential. From this, what you get, energy is equal to energy, potential energy a charge gets is equal to Q into V. So please get this, get the difference. Q into electric field will give you force, charge into potential difference will give you potential energy. Also, we have seen that electric field strength is also negative of change in potential by change in distance. Okay, electric field is in a direction of decreasing electric field. That is why if you have got plus 10 volt over here, plus 2 volt over here, potential is decreasing this way to the right, so the strength of the electric field direction is to the right. If you have got 0 potential here and 5 volt potential here, plus 5, which way is the electric field potential increasing? This way is the potential decreasing, so that is the direction of the electric field. All right, so that we have seen. And from this formula, we get electric field strength is equal to change in potential by the distance between them, or E is equal to V by D. Okay, V by D. So these are the formula which we learned in electricity, and also we have applied all these things to capacitors, and we have seen how capacitors gets charged, the graphs, etc., etc. Are you revising them? Okay. So when I finish the syllabus, if you want, I will go over that again, okay, to check whether that's done. Okay, first let me finish off with the syllabus. Then this is Coulomb's law. This is Coulomb's law. What is there tough? Final equation. This is the final. This is the. Okay. So once I finish with that, I will, when I do the participles, hopefully it will be clear. Okay. All right. Okay. So now, having known about all these things, we are going to see another one, which is magnetism. Okay, magnetism. In that, so we will see what causes magnetism, or how magnetism is produced, how and what is magnetic field, what is magnetic potential, etc., etc. And what are the, and then we will learn about electromagnetism, where electricity and magnetism separately. Okay. So first of all, what is magnetic field caused by? Magnetism caused by. We will learn in detail that magnetism is caused by moving charges placed. Okay, moving charges. Okay, moving charges placed. Yeah, in a magnetic field, or moving charges will always cause a magnetic field. Now, magnetism is also caused by bar magnets, which you are familiar with. Bar magnet. And what is a bar magnet? It has a fixed north and south pole. Just like you have got positive and negative charges, each charge has an electric field around it. If you place them closer, they have got a combined electric field, and the electric field lines are from positive to negative, from positive to negative. And the strength of the electric field at a point is E. Similarly, if the magnetism is produced by bar magnets, they have got north and south pole, two dipoles. Here also you have got positive and negative charges. They are called electric dipoles. They are called magnetic dipoles here. The magnetic field near to every bar magnet or permanent magnet or any magnet, there is a magnetic field around it. And that magnetic field, pattern of the magnetic field line is from north to south outside the magnet, but it is south to north inside the magnet. They're closed continuous curves. Okay, so the magnet, so but here it is not closed. Magnetic electric field lines are not closed and continuous. This is one major difference. Okay, they are not closed and continuous. They always, whether between them or outside, they always start from positive. But here there's a difference. Outside the magnet, it is from north to south. What is from north to south? The direction of magnetic field. While inside the magnet, it is from south to north. Why? Because magnetic field lines are closed and continuous. Of course, yes. Any electric, any fields, they do not intersect each other. Also, if they are crowded at a place, if they are crowded, that means their strength is more. If they are far apart, their strength is less. All those things are common. This is the only difference between. Okay, all the other. What? That one. V is equal to V naught e to the power minus T by RC. Yeah. So this you have to practice because you are not so familiar with doing exponential calculations, right? That is why. So, but it will become easy if you keep doing a few questions based on that. It's not that difficult. Okay. Okay. But then when I finish the syllabus, I'll go over that again if you want. Okay. So now this is the major difference. Now here you have got every point in the electric field has electric field strength. E is the electric field strength. Similar, just like that, around a magnet, every point has magnetic field strength. The magnetic field strength. Another term is magnetic field intensity is represented by the letter B. Okay, magnetic field intensity is represented by the letter B. It's a vector quantity, just like electric field. It's a vector quantity, and its unit is Tesla. Tesla. Okay, so magnetic field strength is represented by B, and it's a vector quantity just like electric field. That means, and that means it has the direction, and the unit is Tesla. What is the unit of electric field strength? Electric field strength, you can understand from the formula. Electric field strength is equal to force by charge. Force is Newton, charge is Coulomb. This is one unit. Also, you know, electric field is equal to V by D. Using this formula, the unit is volt per meter. So this is another unit of electric field. Electric field has two units, Newton per Coulomb or volt per meter. But magnetic field has a unit which is Tesla, or when you break it into basic units, it becomes Newton second by Coulomb meter. Okay, Newton second by Coulomb meter. So this, please remember, electric field strength is represented by E, but magnetic field strength is represented by B. Okay, so now what is the direction of the electric field? Electric field direction. If the electric field is in this way, what can I draw over here and over here? Electric field is caused by charges. So, but see, electric field is caused by charges. So you should not put on that. So positive to negative. Okay. Similarly, if I say magnetic field B, how do you know that it is electric or magnetic field? By the letter. E is electric field strength, B is magnetic field strength. If this is the direction of magnetic field strength, what is over here? What is over here? Here north, here south. Okay, so that you please understand. If the magnetic field strength, if this is B, if the B is in this way, what does that mean? That the top north. Okay, so also now many a time north and south poles will not be given to you because you are in A level. There they will only give you this. So to do certain questions, you need to know that what is over here, what is over here. Another way of representing magnetic field is into the page. If they say this magnetic field B is into the page is represented by cross. Into the page. What does this mean? Where is the North Pole here? If this, no. Here you don't have to apply that. Now the magnetic field is compared to this paper plane. I'm saying magnetic field is represented by a cross. What does this mean? This means into the page. That means like this, into, perpendicular to this. So this is the direction of magnetic field. If this is the direction of magnetic field, what pole have I placed over the top of the paper? South, north. Do you understand? Into the page means north pole above paper, south pole under the paper. Okay? Out of the page is what? A dot in a circle. How do you know? You think about a dart. What is a dart? You got a pin and 4 flaps, right? The one that you throw to dart boards. So this now, imagine that you are placing a dart in the direction of the magnetic field. If it is into the page, this will be the pin will be touching the paper. Here, when you look from here, what do you see? The 4 flaps you see? These are those 4 flaps. We can remember like that. Similarly, if it is placed out of the paper, if it is placed out of the paper, you keep the dart in the direction out of the paper like this. What do you see on the top? The point. That is why out of the paper is represented by this, into the page by cross. Okay, this is easy to remember. Okay, fine. So now if it is into the paper, that means North Pole is above. If it is out of the paper, North Pole under the page, South Pole above the paper. Okay, so these are different ways of representing magnetic field. Now we have to learn what is magnetic flux. Flux, magnetic flux. This term is new to you, but it is easy to remember. Listen, assume that these are some magnetic field lines. Okay, magnetic field lines. They are parallel, equidistant. How do you describe this magnetic field? They are parallel and the distance between them are equal. How do you represent them, or how do you describe them? What kind of a field is this? And I've written B. What kind of a field is this? Okay, fine. It's north to south, but this parallel, equidistant lines always show uniform field. If it is B, uniform magnetic field. If it is E, uniform electric field. Yes, but for electric field, what will you write? E you will write. Magnetic field we will write B. Okay, so now you listen. What is flux? So assume that I've got parallel magnetic field lines like this. I'm placing a cardboard. Okay, I'm arranging them in different orientation. In the first orientation, I'm keeping the cardboard this way. That means like this, so that it cuts through the field lines. The field lines are like this, and I'm placing the magnetic flux this way, so that my cardboard can cut through. In this case, if this is my cardboard placed exactly vertical, how many lines are actually passing through this cardboard area? Okay, this cardboard has an area this much. I'm placing it over here. How many lines are actually passing through? That is called a magnetic flux. So magnetic flux is the number of magnetic field lines passing through certain area. Okay, number of magnetic field lines, it's a count, 20, 30, 40. Number of magnetic field lines passing through certain area is called magnetic flux. All right, magnetic flux. Now in this case, if I keep like this, the flux is maximum. What if I keep my paper this way? How many lines are passing through? No lines. So that means if I keep my area here, no lines are passing through, therefore flux is 0. What if I keep my paper this way? At an angle, same area I'm placing at an angle, say this much. 1 and 2 has passed. Okay, so assume that the angle between them is theta. Angle between the paper and this is theta. How many are actually passing through? For that, you have to take the vertical component. This one has a horizontal component and a vertical component. Vertical component is the one that is passing through. Therefore, vertical component is sine theta. So in general, we can write magnetic flux phi. Which letter is this? Phi, phi, Greek letter. Magnetic flux is represented by phi. Phi is equal to B. What is B? The magnetic field. No. Strength. Phi is the number of lines passing through. B is the magnetic field strength. B into area of this paper or the cardboard into area of the paper that is kept in the magnetic field. So be a sine of theta. Very important. Okay, magnetic flux is represented by phi. That is equal to magnetic field strength. And why we take only one value? Because it is uniform. The strength of the magnetic field at every point is same. Multiplied by the area, multiplied by the sine of the angle between them. In this case, what happens? The first case, this is 1. In the first case, what is the angle? Theta is equal to, what is the angle between this and the magnetic field line? 90. Theta is equal to 90. So sine theta 1 sine 90. How do you remember? How do you remember sine values? How do you remember sine value? You think, okay, without memorizing, you think about the sine graph. What is a sine graph? What is a sine graph? A wave. Sine 0. 1 minute. Let me get something. 360 is plus 1. So when I ask you sine or cosine values, have this picture in mind, answer quickly. So if this is a magnetic field, okay, if the paper is placed at an angle, say for example like this, this is the paper, this angle is theta. What is a flux? Phi, magnetic flux. Magnetic flux linked with one area is equal to BA sine theta. All right. Now, if I keep the paper this way, same area this way, what is the angle? Angle between the paper and the field lines is 0. Sine 0. 0. Therefore, flux phi is equal to BA into 0. 0. No lines are passing through, no flux is linked with this. In simple terms, that this paper orientation is not cutting through the field lines. If it is placed like this, if the same area is placed like this, this is the A, this is the A, this is the area. Here theta is equal to 90 degree, this angle is 90 degree, then sine 90, 1, therefore flux is equal to B into A. So this is the maximum value of flux. Okay, so you learned a new formula. Flux phi is equal to BA sine theta. So this is the flux connected to, or the field lines passing through one area. one area. Assume that I've got 10 such areas, 10 papers placed in the magnetic field. If there are n number of papers, n number of areas, okay, so this is for one area, means maybe one coil. So if there are n number of coils, which usually happens in practical cases for motor and all, okay, for n number of areas or coils, we say a coil. Even though this is hollow, this is considered as an area. For this, that means this is if you have got one single coil. What if you have got multiple coils like a spring? N number of coils. This area of each one is one A. There are n A's. So for n number of coils, the flux linkage is called, we say flux linkage is equal to n into phi, which is equal to n into b into a into sine theta. Okay, whenever we talk about motor or anything, we talk about this flux linkage. So area, we assume all the coils of same area. For example, in a spring, usually all the coils of same area. Okay, and what is a flux? Magnetic flux phi is a scalar quantity. Why? Because it's just a number, it has no direction. And what is the unit? Is Weber. Weber, WB. Weber. Okay, a new unit. And 1 Weber is equal to what? Weber is equal to what is the unit of magnetic field strength? Tesla. And A is meter square. So 1 Tesla meter square is equal to 1 Weber. Okay. Exactly. Instead of n, that the length may tell you how many coils are there. Because they are all, a cylinder could be considered as many coils placed one over the other. So the length, this length, how many coils are there? That B part. No, look here. If you have got one coil of thickness, maybe now we usually talk about a spring, okay, which has certain length, and we know the width of one coil. So the total length divided by the width of one coil will give you how many number of coils. Okay. Okay, see, look here. If you have got one coil, you have got only one area. One area. If you have got a spring, assume that it's like this. It's like this, placed very, very close. This is the area that we are talking about. But how many? So if you know the thickness of one coil, if you know the total length L, then N is equal to total length divided by thickness of a coil. Thickness means this thickness, okay, thickness of a coil. All right. magnetism. Okay, which is magnetism caused by or due to electricity. Electricity can cause magnetism. Okay. Okay. Magnetism due to electricity. This is what we are going to see. Magnetism due to electricity. First of all, we are going to see the motion of a charge in electric field. Now, this was first discovered by whom? First discovered by Christian Oersted. Okay, that means what he did was, he simply passed, he was doing some other experiment, there was a wire, he was passing some current through a wire. This was the table. Okay, and he held a, no, DC current, DC current. There was a magnetic compass placed nearby. It was on the table. He did not put that, but it was there. But he noticed that every time he switches this on, now before he switched this on, assume that the magnetic needle was pointing this way. The moment he switches it on, this position changes to some other position. Maybe like this, but to some other position. Okay, so that means this is a magnetic material. It will move only when there is a magnetic force. There was no magnet placed close by. So this experiment made him think that when current is passed through a wire, this wire becomes a magnet. Okay, the wire becomes a magnet. So this was the beginning of electromagnetism. We are going to see, we are not going to start with a wire, we are going to start with the basic thing, a charge. Okay, a charge. When a charge, okay, when a charge is placed, okay, see, look here. Okay, when a charge is placed, okay, I'll give you a table. Okay, if the charge is at rest, if the charge is stationary, okay, stationary charge, what does that mean? You have got just a positive charge. Stationary, how do you represent? V is equal to 0. That means it is at rest, not moving. Speed is 0. That means it's not moving. This one has only an electric field around it. A stationary charge has only electric field. Okay, a stationary charge has only electric. It produces magnetic field. Okay, this is very, very important. If you place some charge at rest, it has no magnetic field. If you place some charge, it has only electric field around it, no magnetic field. But the moment you make a charge move somehow, it has electric field plus magnetic field. You understand? So that is why, and if it has magnetic field, then this will have some magnetic force. Okay, if it has magnetic field, that means this is like a magnet. Only magnets have magnetic field. A moving charge has magnetic field. Moving charge has magnetic field, which means there is a magnetic force produced, okay, on this one. So magnetic force by the magnetic field, FB we write, FB. This can be calculated by B, which is a, okay, B Q V sine theta. Okay, B Q V sine theta. So this is the force produced by a charge when placed in another magnetic field. So since, okay, see, look here, where do you get this one from? If you have got just one magnet, north south, will this magnet move? No. This creates a magnetic field. In the field, if you place a moving charge, there is magnetic force FB. And the strength of the magnetic field, this is caused by this one. This is causing a magnetic field, and every point has the magnetic field strength. So the force, this magnetic field caused by this one is pushing this one. With what force? The force is equal to BQV sine theta. Only electric field. But a moving charge can produce electric field as well as magnetic field. Now, if you place this charge in another magnetic field, for example, assume that this is a north pole, this is a south pole. You place the charge which is at rest. Nothing will happen. Okay, to this, nothing will happen. Why? Why? Because there is, this is at rest. This is at rest. It has only electric field. Electric field and magnetic field will not interact. Only two electric fields interact or only two magnetic fields interact. You got it? Between the north and south, which field you have magnetic field? This one has no magnetic field, so no interaction. That if you have got the same north and south, the same charge, this one, plus you made it moving. Okay. This is somehow moving. It is moving to the right. So in this case, there is a velocity. This is a moving charge. Okay. This is a moving charge placed in external magnetic field. What do you mean by external magnetic field? This magnetic field is created by these two. So this is the magnetic field. Okay. So this magnetic field is produced by this one. So this is called external magnetic field. Okay. Now this, since this is moving, it has its own magnetic field. It is like there is one magnet here, another magnet here, north, south. This has its own magnetic field, this has its own magnetic field. When you place two magnets closer, what will happen? Either they attract or they repel. Okay, 1 minute. Okay, so either they repel or attract. Why? Because there is one magnetic field here, another magnetic field here. When two magnetic field lines interact, there is a force. That force is equal to this much. Okay, I'll say once more. When two magnetic fields, what are the two magnetic fields here? Magnetic field due to a magnet due to a permanent magnet and magnetic field due to moving charge. Okay. Somehow, that means two bar magnets, what will it do? Same thing will happen if you place a charge near to one of the magnets. Moving charge near to one of the magnets. So when two magnetic fields interact means that when they come closer. That means magnetic fields from two sources come closer. And this is an example. This is creating an external magnetic field. And when any charge moves, it has automatically a magnetic field created. Or this charge is now like a magnet. Moving charge is like a magnet. Okay, so this is one magnet, this is another magnet. There are two magnetic fields placed in one place. So what will happen? That's called interact. When two magnetic fields interact, what will happen? They produce a net force and makes the charge move. Which way? In the direction of net force. Okay, this is motor effect. Motor effect principle. Okay, somehow if you create two magnetic fields, and if you place them closer so that the two fields can interact, they will produce a net force. That force will make that charge or wire or whatever it is move in the direction of the net force. Okay, and how much is that net force? Now, since it is a charge, force due to magnetism B is equal to BQV sin theta. This is the formula. So what is this? The force on a moving charge in magnetic field. So force on a moving charge, which is Q, in an external magnetic field, which is B. Are you getting this? Force on a moving charge placed in an external magnetic field is equal to, we write FB, is equal to BQV sin theta. Very, very useful formula. Okay. Now this one has, and what is the maximum force this one can have? Sin theta is 1. That means BQV, maximum magnetic field. Not magnetic field, force. Maximum magnetic force is equal to BQ. Clear? BQV. Now second one. When a current carrying wire. What do you mean by current carrying wire? What is inside? When if you have got a wire and if you connect it to a battery, what happens to this wire? What is moving? Charges are moving. Okay. So this one, when you pass current, that means the charges are moving. Q are moving. Charges are moving. Now, if you place a magnet nearby north-south, this magnet will create what? External magnetic field. Okay. Moving charge will create what? Moving charge will create and a magnetic field, another magnetic field. So please try to understand why two magnetic fields are produced. Exactly. Okay. Now, if it is through a wire, earlier you had the charges separately. Now what you are doing, you are placing the charges inside a wire and you are making the charges move at a constant speed. In that case, when a current carrying wire is placed in a magnetic field, then the force on a current carrying conductor is equal to BIL sine theta. But another formula. What is this? This is for the current carrying wire. If the current is I, if the length of the wire is L, the strength of the magnetic field is B, then you can use this formula BIL sine theta. Theta is the angle between the current direction. Assume that this is the magnetic field and I place the wire like this and here I connected the battery. So theta is the angle between the electrons. The electrons are moving in this way. The electrons are moving in this way. Okay, because positive, no, yeah, electrons are either moving like this or like this. So I is the current passing through and L is the length of this wire. Okay, L is the length of this wire. A wire placed in a magnetic field, then the force is this much. Okay, now third case. Instead of the wire, now this is used in a motor. Okay, not this one, that's the next one. Instead of the wire, when a coil, okay, instead of this straight wire, if you bend it into a coil, when a coil carrying current is placed in external magnetic field, then the force on the coil is equal to B A VIA sine theta. What was the first one? BQV sine theta for a charge alone, BIL sine theta for the straight current, and if you've got a coil, okay, if a coil, this is a wire, if a coil of area, okay, if this is the coil, this area is A. So circle. Now, yeah. First, no, the cross-sectional area means this one. This is the area. Okay, so please note it down, the three formula, and quickly study that now. This is about magnetic fields. Now what? Okay, let me summarize again. You got a charge which is placed in, say, electric field, okay, which is placed in, say, electric field E. Okay, and this we did already. So if it is at rest, nothing will happen. Okay, if it is moving, now That means what? This is positive, this is negative. A positive charge is repelled by this, and okay. So what is the force it experiences? This charge will experience, because of the electric field, it experiences a force which is Q into V. Yeah, this we did. Electric field strength F by Q. So this will experience a force which is Q into E that causes the charge to accelerate. So what is the acceleration of the charge? Force by mass, which is force is equal to QE by M. No. Mass of the charge. This charge. Okay. If you know the acceleration, you can use equations of motion to find the rest. What are the equations of motion? Yes, V is equal to V square is equal to, okay. Oh, sorry. Take it back. So this is very important. If it's an electric field, it experiences only electric force. Okay, so what happens? Its speed will increase. Speed increases, or we say accelerates. How much is the acceleration? This much. Okay. Now, so either you can explain like this, or you can say this is positive, positive and positive repel. This is negative, negative and positive attract. Charge and magnetic force are totally different. It's like you're comparing a plant with an animal. They don't have any connection. The only connection is that when the charge is in motion, it produces magnetic field also. This is the only connection. That means if you can make a charge move, you are creating magnetic field. Yeah, so there is a magnetic field produced, and the force and the force due to magnetism is equal to BQV sin theta. Yeah. Okay. That we can assume. Like instead of a charge, if you have got a coil of wire, we can easily find that. Or we can find the force in this acting. If the magnetic field is this way, if magnetic field is that way, that means this is north pole, this is south pole. If you have got a point charge which is moving, that means this has a magnetic field around it. So these two magnetic fields interact, and the force produced is equal to BQV sin theta. Instead of this charge, if you are making a wire move through which electrons move, then the force is equal to BIL sine theta. If you have got in the same magnetic field, if you have got a coil of wire placed, okay, in that case, the force produced is equal to BIA sine theta. Exactly, yes. See, that is difficult to say if unless it's a coil of wire. But that can be produced by this formula F is equal to Q into B, yeah, Q into V cross B. Okay, there is a cross method problem to know what is the direction, but still you don't, this is the direction of the external magnetic field. Okay, yes. So is this much okay? In an electric field, only electrostatic force. In a magnetic field, a moving charge has both electric and magnetic. Okay. Now this is if we place an electric field. What if we place a magnetic field as well in the same place? If you have got magnetic field as well, then what happens? Then the electric field will try to bend in one direction, magnetic field will try to bend in another direction, and if it goes straight, you can say QE is equal to QVB. Yes, in the same place. Okay, if you apply both at the same time, there is electric field as well as magnetic field. Okay, yeah. Yes, a motor effect. Now, one more thing that you have learned. This, what is the direction of the force? Assume that you have got magnetic field this way. And you are placing a charge which is moving this way. What is the angle between them? What is the angle? 0. So BQB sine theta. So sine 0. Sine 0. 0. So if they are parallel, no magnetic force. If this is a magnetic field and okay, now if it is at rest, there is no force. If it is like this, that means this is the north pole, this is the south pole. If you place a charge in motion, if a charge is already like this, magnetic field is in this way, and this is also this way, then they will interact, produce a net force, and the force will be always perpendicular to its velocity. I'll give you another example. Assume that this is an into the page magnetic field here. Okay, this means magnetic field into. To this, I'm applying a force. Okay, so now here, if a positive charge enters with a velocity, can you imagine? Positive charge is coming in this space with a certain velocity. Now, this is the direction of velocity, this is the direction of magnetic field. What is the direction of the force acting? To find, yes, force acting on a charge, force acting on a charge placed in magnetic field B. What we have to do? Use Fleming's left hand rule. Fleming's left hand rule. What is Fleming's left hand rule? What is Fleming's left hand rule? No. Fleming's left hand rule says that if the first finger shows magnetic field, first finger for field, second finger for current, current is from positive to negative, then the thumb will cause a force. Thumb will cause a force. So now apply that over here and find out the first finger for okay, let's see. Left hand rule, first finger for field, no, first finger for field, second finger for current. Yes, that means to this one, when it comes over here, it is already moving, but there is a force in this direction. Okay, so that is why I told you this is perpendicular to the velocity and magnetic field. So this way. Now it is already moving here, but now a force is applied. So which way will it go? It will go in the direction of the net force. So the particle comes over here. Here also its velocity is this way, but there is a force acting to the center. There is a force acting to the center. Okay, and that force is perpendicular to the velocity. Therefore, it goes in a path like this. Okay, earlier it was like this, then it goes like this. Then here also there are, okay, so like that, here the velocity is this way. Then when it comes over here again, the velocity is this way. Like that, if you take innumerous positions, what is it finally reaching to? All the magnetic forces are to the center. All the magnetic forces are to the center. That means this will move in what path? Circular path. When will it move in a circular path? Very important. If the velocity is perpendicular to magnetic field. If the direction of motion is perpendicular to magnetic field, what will happen? The charged particle will move in a circular path. Because why? Because the force will be always perpendicular to velocity. All right. So what will the magnetic field do? So magnetic field will only, please remember this one, we need later, will only change the direction, make it go in a circular path. Magnetic field will only produce circular motion, only change direction. Yes, yes. No acceleration. Very, very important point. Huh? Yes, yes. I'll come to that part. Yeah, wait. I'll come to that part. Okay, so please go through this again. Take a minute to understand. When a charge is moving perpendicular to magnetic field. Perpendicular to magnetic. For example, assume that the magnetic the magnetic field is this. What is this? What is this? No. If this is the magnetic field and a positive charge is moving with velocity. Velocity is this way, magnetic field is this way, so the angle between them theta is 90 degrees. In that case, we have found that there is a force perpendicular. Force is perpendicular to velocity, so it will move in a circular path if there is magnetic field here also. It will move in a circular path. What happens? The particle will move in a circular path. Very, very important. When the velocity is perpendicular to magnetic field. Okay, it will move in a circular. It will move in a circular path. The word circular should tell you that there is a force necessary for any object to move in a circular path. For any object to move in a circular path, what it needs? It needs what? Okay, now not magnetism, anything that is general. Centripetal force. Centripetal force. Centripetal force. And that is provided by what? That is provided for this charge also to move in a circular path. It needs centripetal force. That is provided by what? By the magnetic force. Very, very important thing. Okay, very, very important. Study this thoroughly again, because this is repeated in the next chapter and the last chapter as well. This concept. When a charge is moving in a magnetic field, it will move in a circular path. If it is moving in a circular path, it needs centripetal force. This centripetal force is supplied by the magnetic force. So we can write centripetal force, say Fc. I'll write Fc here. Is equal to magnetic force. I will put Fb. Fb. What is the formula for centripetal force? First chapter. Centripetal force. mv square by r is equal to, what is F force due to magnetism on a moving charge? BQV. Okay, very, very powerful equation, and this will help a lot of things. This will help you to calculate what are the things. First of all, okay, from this we can calculate number one, the velocity with which it is moving. The velocity with which it is moving. So from this, Fb, you start like this, is equal to Fc. BQV is equal to mv square by r. V and V cancel. Therefore, V is equal to this. V is equal to BQR by M. No need to memorize this. Only memorize this. Okay. Then you cancel and rearrange. This is equation number 1. All right. Then if you know V, this is the linear speed. This is the linear speed. That means it is the speed with which it is moving. This velocity is V. If so, what is angular velocity? If you know the linear velocity, angular velocity is what? Angular velocity omega. We know that omega is equal to V by R. Do you remember this? Or V is equal to R omega. In the first chapter we learned. Okay. Therefore, omega is equal to V by R. If this is V, what is omega? BQR by M by R is BQ by M. Okay? Huh? Yes. If you know angular velocity, third one you can find the time period. Time period, capital T. What do you mean by time period? Time taken to make one oscillation. The time for this. Time to complete one oscillation. What is the formula? Omega is equal to 2 pi by time period. Therefore, time period is equal to 2 pi by omega. Therefore, time period is equal to 2 pi by omega. Omega is BQ by M. Like I didn't count, but that's why I told you to make formula sheet. Huh? Omega we have V is equal to R omega, V is equal to 2 pi by T. These two. Okay. Now, okay, please write. Now, this is very important. Why? Time period is equal to 2 pi. This is a constant. Mass of the particle is constant. Magnetic field which you have applied is constant. Charge of the particle also constant. Okay. What does that mean? That means time is constant. Time period is constant. Which means if you have got a magnetic field like this of B, if it moves in a smaller circle or if it moves in a larger circle, time period in both circles are same. It is independent of the radius. Time is independent of radius. Very, very important thing. If it, that means there is no R in this equation. If this one had an R, then it will be depending on R. Okay. Then how is that possible? How is that possible? It takes the same time to move a smaller path or a larger path. How is that possible? That means here it is moving faster. The linear velocity, say v1, its velocity v2. Here this is traveling faster. Okay, so this one is same time. This is traveling slow, but both completes circle in same time. Velocity is different. V1 is greater than V2. This is V1, this is V2. Larger circle means, see, look here. When the radius increases, velocity increases. Velocity is directly proportional to radius. That is applied over here. And the time period is constant. Okay, will you remember all these things for the next topic? Cyclotron, you need all this. In that time, I won't be teaching you this. Huh? So that is why please study every day. Huh? And start revising. Why? Since we started late, I don't have time to give you a. Okay, so this was what? Motion of a charge, only one single charge in a magnetic field. So force due to magnetism on a charge. Okay, when charge is in magnetic field, force due to magnetism is equal to BQV sine theta. When current is in a magnetic field, if you have got only charge Q, if current is in the magnetic field, the force on the current carrying wire. Okay, that means you have got a wire which has current in a magnetic field. So assume that this is the magnetic field. This length of the wire is important. This length, B instead of Q, I L sine theta. Now, if you have got a coil in a magnetic, I is the current, length of this wire. Now, instead of this one, what if you bend in the form of a loop? What if you bend in the form of a loop? Then the force due to magnetism on the loop is equal to BIA sine theta. BIA sine theta for one coil. If you have got many, N. You know how you got this? You know how you got this from this? How? So FB is equal to BQV sine theta. Now for the charge. Now if you divide it by time, for the current, what is current? Charge by time. Okay, for the second one, current is equal to charge by time. So that means second one, FB is equal to BQV sine theta divided by time. Okay, current is equal to what? Yeah, BQV. Now, yes, now we multiplied by time. Okay, B into, okay, I'll write this and I'll see how you get this one. So this I is what? Q into T. I is equal to Q into T. So that means here, see, you just understand like this. Here charges are moving in certain time. So this can be velocity is equal to what? Length into time. this velocity is equal to distance by time. Distance is length. V q into velocity is equal to distance, length by time into sine theta. Now you rearrange B into Q by T into L sine theta. Q by T is I. That is why you get BIL sine theta. Okay. Now, this is a principle for a motor. Now that I am going to teach you. This is the principle for a motor. In a motor, what you have? You just have a coil of wire instead of this. That's all. We are going to learn about DC motor. Yeah. Shall I start? I'll draw the diagram now. I'll draw the structure and the